Good evening, everyone. I'm Gautham, co-founder and CEO of Polkadex. I believe it's been a long day today, and everyone is tired. I know that, so I will try to keep it short. But the content is really big, what I'm talking about, and it's especially important for people who are working on the projects that involve IPFS and all other off-chain stuff. And so the talk will be about how can you build that off-chain logic and make it part of the Substrate, a node or the Polkadot node or the parachain node that you're running, and secure it better. So that's the talk will be about. So we know there have been multiple talks so far in multiple events talking about Substrate and Frame and what is possible inside that. We know that there is balances, assets, transaction management, contracts, all the other stuff the Frame palettes provide. So there are a lot of functionality that's built in to the Substrate ecosystem. And also it provides a wide range of cryptographic functionalities, namely SR, ECDSA, all these stuff. But the thing is, the main benefit of using Frame is you can simply focus on your business logic, and the team from Parity and Substrate takes care of how to make it secure. They take care of storing it in database, tree management, all the things that Bastian and the previous speakers talked about. And we don't need to care about all those things. We just simply focus on the business logic. So that's the big benefit of using Frame. And again, even if we need to do something that is not possible on-chain, we have off-chain worker. It's a limited, it's a constrained environment still. We can do a lot more than what's possible inside a runtime. So that's good. So this is what's possible with Substrate and Frame inside the runtime, the Frame runtime right now. So let's talk about the limitations. So the problem here is there are certain libraries that use the Rust standard library and a lot of other other dependencies like C or some other language, foreign function usage, which is not supported inside the runtime. And there are situations and business use cases where you need to use this library to provide certain optimizations or provide certain support, but you can't use it in Frame or inside the runtime. And then off-chain workers. So at this point in time, using off-chain workers, you can make HTTP call, Rust calls, and get data from outside. But again, it's not exactly like having a fully fledged networking stack. You still need to, you simply can't do it in off-chain worker context. And yeah, then there are a lot of cryptographic primitives supported by Substrate officially. But for example, BLS is still not supported officially. We need to wait for the official support. Or you have to fork the existing libraries and then somehow make it working inside the runtime. So it takes a lot of effort. And also, you're risking the production, how should I say this? When you fork some library, then there are higher chances of introducing a mistake and then reducing the security of the library. So that's also there when you fork and make, you try to convert a library and make it work inside the runtime. And above all, yeah, we all know runtime is, for every change, it's limited by the block time. So you cannot have very long running task and pretty much limited on the computation side also. So these are the general limitations of having runtime or the off-chain workers. But then, what can we do? At Polkadex, we wanted to build an off-chain order matching engine that provides sub-second latency and all this stuff. So we resorted to using Intel enclaves to make this happen. But the problem is, working inside enclave is also similar to runtime. There are a lot of restrictions. We pretty much cannot use most of the libraries out there. So we thought about what can we do so that we can have general computation done outside, and then that can be verified on-chain. So that's when we thought we can modify the validator side code. So there's something called Substrate client modules. Yeah, so this is the problem statement. So as I mentioned, there should be some mechanism by which we should be able to do general computation in Substrate, which is not limited by runtime or the WebAssembly or the WASM runtime, and still we'll be able to secure it, just like it's happening inside the runtime. So that's the problem statement. How can we do that? So yeah, in our order book, we have this option order book which has the order matching algorithm, which is basically like matching two orders, making sure it has the same thing, updating the balance. Normal, like pretty basic stuff. But then we couldn't do it in runtime because we were using a lot of libraries that cannot be compiled to WASM, and it has a lot of foreign functions, and it's simply not possible. We had two options: either simply use that library somehow, or we modify it, create that particular library that we want to use, fork it, modify it for make it compatible with runtime, the WASM runtime. But again, if you fork something, then you have to maintain it. Like every time the contributor of the original library makes a change, we have to again make changes to our fork. It becomes cumbersome. So that's when we thought, okay, let's take the other route. So the solution is Substrate client modules. So what that basically means is, you can write code that looks like, that's exactly like a normal Rust language. It's not compiled down to WASM or anything else. It just works as normal Rust, but Rust's part of the Substrate node or the validator node. So this really makes sense because, it's running in a non-constraint environment, and it has all the capabilities of a normal Rust program, but it is not secured by anything. It's completely in a sense unbounded. Every validator can modify this code and still the blockchain will function. And it will be tampered also. So that's something this provides. But the main benefit is all networking, block production, and all the consensus stuff is also happening in a similar fashion. So in the morning, we saw about Aura, Babe, and the new consensus algorithm, right? So all that code is written here. So we just need to come up with a way of somehow having a consensus between the validators regarding what's happening on this client-side code, and we can somehow agree, all the validators agree on that, then we can have this information then sent to the runtime. And the beauty is, at this point, the writing, whatever your business logic is writing a consensus layer, because your logic is running along with the consensus protocol, and it also has its own a way to get an agreement between all the validators and all the full nodes. And it allows you to use any libraries and pretty much anything that you can find outside that can compile in Rust can be used here. So how do you do this? So we start with, OK, before I start, unlike other presentations, there are probably 8 slides starting with pure code. So bear with me. So the way we do this is we start by defining a struct. Right in this case, we are defining it as OCX worker. It's basically a structure that will contain all the access points or all the objects required to talk to the runtime, talk to the networking module, talk to all the other stuff that the Substrate client provides. And if you can see, most of the things comes out of the SC client API and SP API libraries. These are the libraries created by Substrate to provide access to the networking code or the full client node that's inside a validator. And we have this struct, and inside the struct, you can see we take a client, backend, runtime, and a bunch of other stuff, which I will get to later. And this basically is the main structure that runs your business logic, and you can have all your variables or the data structures inside this. And the second thing is, it has a new function which accepts a bunch of parameters provided by the validator code. I will get into this, how exactly this new function is called. But in this function, you can see there is client. So client contains a helper function called finality notification stream. This basically provides a stream of events whenever a block is finalized. So this is when the Substrate node runs and the blockchain, the network runs, blocks are generated, grandpa comes into effect, and then the blocks are getting finalized. So every time a block is finalized, now we know a particular state is finalized, and we get a notification here. So this is the driver of your business log. This should be the driver of the business log, because now you have a event every time a block is finalized, and that will trigger your run logic. And that can be used to access the state, the runtime or the state of the blockchain, read some data, do some of your business logic, and then take actions based on that. For example, let's think about this. If you want to use IPFS, and we all know that IPFS cannot be executed inside runtime, right? So you can have your IPFS logic implemented, the IPFS library implemented in this structure, and every time the run function receives a finality notification, you wanna, let's say, pin a particular object in that IPFS node. That can be done here. So that's the whole point, So the end result will be an IPFS node will be running inside the validator node. So in a single binary, both IPFS and your blockchain's validator will be running. The same can be done for full node also. Yeah, so I was talking about the run function. So as you can see, it's an infinite loop. And in that, you take a notification, a finality notification every time a block is finalized. And then you handle that. So inside this handle finality notification function, it can be anything. There is no reason to completely avoid and exclude anything from there, because that's basically your business logic. So every time that function is called, your logic is executed, and you can handle the state. For example, as I mentioned earlier, to pin an object. Let's say somebody sent a transaction on chain saying that, okay, hey, network, I want to store some data from IPFS. This is the IPFS CID. So this run, when that block gets finalized, this function gets executed, and then it will check the runtime state whether a new notification from the user is there or not. If it is there, it will take the SID, and then that gets pinned using a local IPFS node. So similar to that, pretty much any logic can be executed here. Yeah, so this is how you take data from the runtime. So when you write logic in this manner, you need to take into consideration that all the validators will be running this piece of logic in their own way. What that means is, even if you ship out a particular logic, there's a high chance that since it is open source, these validators can modify the logic and then still run it. Unlike WASM, unlike the runtime where the WASM code is stored inside the hash map or the key, the database, this can be modified, and no one will never know. So there should be some mechanism to identify, it depends completely on the business logic that you are writing, because sometimes it cannot be verified. So there should be some mechanism that you should put on your network so that the runtime can verify, everyone is running the same logic and nobody is tampering with the logic. And so so you should be some way to identify who all are the current validators at this point in time. So whenever the new finality notification comes in, you want to handle a new finality notification, and then you want to, is there an echo? It's fine? Yeah. So yeah, so you're saying, so new finality notification comes in and you want to read some data, and let's say you want to read what's the current validator set from the runtime. And validator set, by validator set, what I mean is, who all are the current validating authorities, and what are their addresses or the cryptographic public keys. So this is how you can take it. It's an example for reading data from the runtime, because here you can see there's a function which takes the header, and it also takes at what block hash, that's the at. And it calls into runtime. So you must be remembering this. The runtime was an object inside the struct that I showed earlier. And that contains an runtime API function, which comes out of basically a macro. And you can call the validator set function. And this function is defined in your primitives. You can define a primitives in the runtime code, which I will show later. And from there, you can pretty much get the data. So this is one way of reading data from the runtime. Pretty much all the functions, all the data can be accessed in this manner. Yeah. So let's say now you have something to drive your logic, and then you have some way to read data from the blockchain state. Now you have taken your business decision, you have logic is executed. Now you have some results that you need to broadcast to the network or modify the runtime state, write some data into the runtime. So, and this is the way how you do it. It's pretty similar to how off-chain workers write the data back to the runtime, where you submit an unsigned transaction to the runtime, and you have a bunch of logic making sure that nobody is spamming. And you can, using the validator set I showed earlier, the runtime logic, the validate unsigned function can verify whether this unsigned transaction is coming from a legit validator of the current set. So you create the call that you want to call. So in this case, approve enclave report. I will get into that. In the live section, I will show that. And you take a bunch of parameters for that. This is the transaction that you want, or an extrinsic that you want to call. And you submit that using the submit transaction function, and submits an unsigned transaction. So there is a signature. This is for a given validator. And approver is basically a different name for validator. And those are report, and the other things are the bunch of parameters that you want to send. And using the signature and the approver, the runtime can verify whether the sender who is sending this transaction is actually part of the validator set or not. And then you send it out. And this will go to the transaction pool, and then later gets included in the next block. And this is the way you can modify the runtime state after, based on the result from your off-chain execution. So you have all the runtime logic, and you have all the business logic on your client side. Now you need to put it together so that this works together with the validator node. So in the service file, like there is a service.rs file probably like in your node side of the in your Substrate code base. And there you will get access to all the components, client, backend, task manager, all that object file. So there you create. So the role object provides like a method called isAuthority. isAuthority basically means that if the node is a validator. So when you start a Substrate node, you will see that you can put that CLI command or the flag like -- validator. That's how you start the node as in a validator mode. And if that is enabled, this will be true, which means that your business logic should only run if the code is started in a validator fashion, validator mode. So if that is the case, you create the parameters. It takes the client, backend, runtime, and keystore. Keystore is basically a way to access the cryptographic storage, where you can store the private keys and public keys of your current validator, and that's how it is derived. And then you start you provide the handler, the task manager with the handler to your, the worker or the business logic that you want to run. So let me walk you through the code, so it will give a better clarity. Can I? Yeah, so as I was saying, this is the this is a piece of code that doesn't work inside the runtime. And this what it basically does is like it's requesting to the Intel servers regarding a enclave that was enclave report, and it want to verify with that Intel server. And it involves a bunch of like foreign functions, function implementation, and also networking call, and that's why we cannot do this inside runtime. But this is something that should be, a piece of code that should be secured by the blockchain for us, because the off-chain component runs an enclave, and the blockchain need to ensure that it is running the original code and then the original enclave, and it is not tampered with. So using this logic that I mentioned earlier, all the validators are executing this logic on every finalized block and making sure that the report submitted by the off-chain component is secure. It's the same thing. It's correct. It's the correct report. And so yeah, here you can see. So this is a client. Let me show you how this is structured. So we define a new crate called OCX. OCX is it's a random name, nothing much. And then you define the off-chain worker, the struct that we mentioned, the OCX worker, and it takes all the components that we need, the backend for accessing the database and the raw database, and a bunch of other stuff, and the runtime for communicating with the runtime logic. And finality notification, it's another object to to get the finality notification, and key store is where we store the private key and the section keys for for the client side. And yeah, these are like other bunch of business logic related variables that you need to make this work. And signed report is basically a vector of reports submitted by the off-chain component that we are currently working with. And here you can see the handle finality notification. So every time a new block is finalized, this gets triggered, and you can see like it is querying the runtime state to get the current active set of validators for the given block hash. And we check if we have hash keys is a helper function that queries the key store and checks if gets the currently available private key and public key pair. So that's the you remember the section keys that you insert when you start a validator. So it's the same thing here. So that we need to insert a section key for the business logic that you are trying to run here, because every business logic or every client side code can or cannot have private key. If you have, then you have to insert it, and the hash key is basically querying the key store and getting the the authority ID or the public key for the current set of validator if any is available. For example, for full nodes which is not running as a validator, no section keys are available, and the hash key function will return none because there are no section keys or private keys available there. And also for validators who are part of the next set, that is not the active set, but the upcoming set. They will also be, it will be returning, it will be returning none, because the parameter that you're given, the validator set, will be the current active set, and it is not part of the current active set. So it will also return as none. And so yeah, so active contains the current validator set, and then authority and authority index basically contains the public key of the or the section key of the current validator. And this is another runtime storage read where you call into the runtime in your palette, and you call a helper function from the palette, the get unapproved and claim reports for a given block number or the block state, and you get that. And if it is approved, you continue. It's part of the business logic. It's already approved. We don't need to do anything. If it is not approved, we run the code to check. Okay, there was a bunch of code here, that's why they are there. But it's fine. So you basically run the code, your business logic, check everything that you need to check, and then you create a signature, whatever message that you want to send back to the runtime for having consensus between the validators. You can sign it with the section key that you have in your key store. And here we are basically signing the report, saying that, okay, here runtime, I as a validator approve this report, and everything is fine with it. I have checked it. And so that's basically what's happening here. You sign it, and then you call another runtime API or a function called submit approve function. So this is where everything gets together. You have the authority and the signature from the authority, and the rest of the bunch of the message or the data that you need to send to the runtime, and it will send that information to runtime, and it will create an unsigned transaction, and then that will be submitted to the transaction pool, and then later gets included in, as part of the block and modifies the runtime state. So yeah, if it is a bunch of error handling, if the transaction creation fails, and yeah, I mean, these are just error handling, but pretty much that's it. This is very simple, client-side implementation. Now let me show you how it is inserted into the validator code. So if you go to the node, there is if you go to Substrate node template, you will see that a bunch of service files. And if you go to the service file here, so this is the service file implementation. This is where Substrate puts pretty much everything together, the runtime logic, the executor for the WASM, and the consensus logic, the task manager. Everything comes together here. So this is the one file, the glue code, that just combines everything together. And here, So you can see the native executor and the key store client, everything gets initialized here. I hope it's visible. Okay, yeah. The transaction pool, the grandpa, the finality stuff, yeah, all that stuff is happening here. And when you come all the way down, yeah, so this is another example of the networking library, the authority discovery, and the networking library, and everything like a lot of stuff, especially the latest beefy protocol that was used by the few of the Snow 4 team and a bunch of others, which is getting included to Polkadot, which is also written in this side of the Substrate node. And yeah, so the grandpa, these are the configuration for booting up the grandpa protocol, and if grandpa is enabled, and then finally starting the grandpa task. Yeah, so this is a piece of code. So now everything is booted up, like we have grandpa, block production, the block import, networking layer, everything is running. So before it starts, like the final, the Substrate node is fully booted up and then moves on to the normal operating mode, we can start up our business logic. So here you can see we check if it is an authority, if it is a validator, then we take the things that we need, the client, backend, all the piece of code that we need, and then we start our like runner function or the run function for our business logic. And this basically starts the logic and keep the run function. It's an infinite loop. It keeps on running until something fails. And one thing to notice here, like it's a spawn essential handle. So what that basically means is, if this task fails for some, like if it panics or it exits without the task manager stopping it, then the entire node is taken down, which means that the entire node will crash. So you can, there is other option also. It's called spawn handle, which basically means that even if this task fails, the node will keep on running. So depending on your business use case, you can decide which one to use. But I will go with essential handle, and it's a blocking function. So we spawn it as a blocking function. And then, so this is how we put everything together. But let me show you the runtime palette. So this is the palette, the piece of function that's getting called from the validator side. And here you can see the approve enclave. So here we have the approver, which is the section key or the authority ID of the validator who signed the particular report. And report is just a bunch of vector that's used by the Intel and the enclave to attach the the enclave. And the validator has verified this particular report, and the signature cryptographically proves that it has done its work. And here it's an ensure none because it is an unsigned transaction, so we cannot use ensure signed. And so we verify the cryptographic signature, making sure that it was sent by an actual like the approver who is claiming it is from. And then we take the storage item, like unverified report. If it is there, we basically like counting the votes like on all the validators. And we can have all the other logic here, the business side logic related to like how do you handle this data, like other logic to make sure that this is a valid report, or like if some validator like approved a false report and then you need to implement a misbehavior penalty for that. All that thing can be implemented depending on your use case. But like basically like the main thing to focus here is like we are able to send the data to the runtime, and then from here onwards it's just like developing any other frame palette, and then you can take it forward based on your business use case. And yeah, so here I showed the submit approve enclave report. So that's implemented here. It's another helper function on the palette side, where we have the enclave report. This is the extension that I showed earlier, which was created here and send us a submit transaction. And we also have like so. Yeah, and jumping to the primitive. So this is the primitives file where you define like the data types and the structures that you will use across the client side and the runtime. And here you can define the key type that you want to use, like a specific prefix that will be used to use for storing the section keys and the key IDs. And then you can define the genesis authority set, the number 0, the validator. They wait to count the validator sets. So that the validator set ID, and then the validator set itself, which tracks the list of vectors, I mean the vector of the validators and the validator ID. And so yeah, here you define what type of like cryptography or the cryptographic primitive that you need to use for this particular use case. So as I mentioned earlier, like Substrate support like ECDSA, SR25519 and bunch of others. So in this case, use case, I'm using SR25519 as the cryptography that validator uses to sign the data and send it to the runtime. And then you define the data types, like the public key and private key and all the data types for that. And so I don't think I have enough time to get into consensus log and things like stuff like that. But yeah, so this is the main part. So here you declare runtime API. So I have defined 3 runtime APIs. So these functions are available for calling from the client side. So like what I mean by client side here is like in here, the client OCX lib.rs, you can see submit, approve, enclave report. Now that is defined here, not defined, like the primitive of that is, the trait is defined here. So all the functions we had defined here is available on the client side. And the definition for this is actually defined on the runtime, where in the runtime lib.rs, you can implement that particular trait for that runtime, where it is calling into the helper functions from the palette you define. So here you can see the validator set is calling into the validator set helper function from the palette, and submit enclave report is calling the help function that I showed earlier, the submit approve enclave report. So this has been defined here. You can see here. It's a helper function from the palette. And yeah, so pretty much this is it. So if you do all this together and if you define it accordingly, and if you have a mechanism to basically get an agreement with all the, like make sure that all the validators are in agreement with the logic executed outside the runtime, can pretty much implement all the, like pretty much any long running or any complicated logic and still have it secured by the network. So as with the number of validators increase, each and every validator will be running this particular business logic that you write, and that gets if it satisfies the consensus rules and all that protocol that you define, then it gets included into the runtime. Can we go back to the slide? Yeah, so there are a few things to note here. So the logic that you write is executed by all full nodes and all validator node depending on how you define it. And it will basically fail if the validators don't have either enough capacity to run this. So the thing is, as Gavin mentioned earlier, like there's a 2-dimensional weighting approach for each and every extrinsic that's used in the runtime. And here we don't have that. Like pretty much nothing is stopping a developer from writing like complicated, like an infinite loop basically, can be written here and nobody will know it. So care should be taken on making sure that the validator, the recommended specs of the validator can run this, and there should be some tolerance on how complicated your business logic here is. And also, like in the example that I mentioned, if there are like 100 validators in your network, then each of the 100 validators are going to run the business logic, and if everyone will be running sending an unsigned extrinsic to the transaction pool, so basically spamming your transaction pool. So we need to carefully architecture it in a way that the spamming doesn't occur. At the same time, you have enough mechanism to secure the logic. Another approach that we can take here is using BLS signatures. Like since we can write pretty much any, we can use pretty much any library in the client side, we can have like aggregation of signatures and then maybe like a bunch of validators sending the aggregated signature and the data to the runtime, so that instead of sending like like 100 transactions for 100 validators, we can send maybe like 5 or 10 transactions. And yeah, like we need to come up with like ingenious ways to figure out how to reduce the number of transactions when the number of validators increase. And if you take the example of Polkadot, like there are like more than 1,000 validators there, and then it's basically let's just spams the transaction pool. So we need to keep that in mind. And another thing is, there should be a logic to handle misbehavior. So this is not secured by runtime or the WASM. So what that means is, like, there is no consensus between all the validators on what everyone is running. And you never know, like, if a validator is running a tampered code and then sending some like false reports to the runtime. So there should be some mechanism to handle such misbehaviors, and slash those malicious validators. And what that means, like, you can have like something of for example, like I mentioned the report earlier, like if some all the other validators are also running the same code, and if we go by the game theoretic model, like we assume that 2 by 3rd are running the are basically honest validators. In that case, these the majority of validators can dictate false reports being submitted to the runtime, and runtime can take actions based on that, like slash the stake of that particular validator. I haven't shown that here because it's a lot of things, but that's something that we can actually do to de-incentivize modifying the client-side code. And what's the case of a parachain? So if you're a parachain, the logic that you define in such fashion is not secured by the relay chain. So it's completely depending on your collator. And if you're just running the bare minimum collators, you're basically risking your chain and risking your business logic. So yeah, so that's a big problem here. And then again, validators and collators are doing extra work here, so and they're not compensated in terms of transaction fees or anything. So there should be some changes in which how we reward their effort on this, because they're running extra piece of logic that is not accounted for. It's completely unbounded, all this stuff. So yeah, so with this particular approach, we can basically run like any logic out there, and then we can have it secured by the validator network, and basically like we can build new use cases, like especially I mentioned about IPFS and all the other stuff. We can run, all the validators can run IPFS nodes along with the Substrate node without having like RPC calls with each other. We can use this, but again, when you run an IPFS node, there will be a lot of storage costs, like storage of the validator will increase, and extra networking, the bandwidth usage will increase. So we have to take into consideration the extra effort put by the validators, and carefully design business use cases. So this basically opens up like a lot of opportunities here, and we can build a lot of stuff that's really interesting. Especially this is one of the things that made Polkadex possible, because we have a off-chain component that runs outside the system, which provides the low latency and everything that we need. At the same time, with this, like, it's not like the off-chain component is like a trusted or anything, because whatever off-chain is doing is again done by the it's verified by the validators, checked, and eventually, like, we are also planning to completely remove the enclave model, like have the general computation off-chain, and then completely rely on this particular model to secure the network. So yeah, I mean, I know it's like a lot of code and stuff. I hope at least a bunch of you guys got what this is all about. And you can reach out to me in Twitter or in our official channels, and then I will be happy to help. Yeah, any questions? Thank you.
OK, if you have any questions, just put your hand up, and I'll come find you. You would be way over there. Over there first.
So do you have any thoughts for the situation where basically we're using parachain? Like solve this problem? Because it's a big thing if you have a parachain.
What do you mean? Like parachain is able to run run logic in the same fashion?
Some tricks or something, yeah.
Yeah, I mean, it doesn't matter. Like, if it is a substrate node, whether it's a solo chain, parachain, it doesn't really matter because it's just, we are adding on to the client side as let's say a sub-consensus protocol, and it doesn't really matter. The main point to note there is, like, the main benefit of having a parachain is that all your state transitions and the runtime and the block production it's secured by the relay chain or the Polkadot, right? So you get to benefit that. But that's not available in this because it's running outside the context of the runtime. I mean, everything that you define on the palettes on the runtime, it's still secured by the relay chain, but all that logic that you have on the client side, the business logic that I showed, that is not covered by the Polkadot or the relay chain. So you have to, it's like a trade-off. Like, if you have a certain piece of code that doesn't need to be secured, in that parachain context, you can definitely run it in this fashion and have like extra edge over, compared to running it in the runtime. But like, if you can come up with some way to securely write that information to the runtime, and then that can be verified by the relay chain, and you get all those benefits. But yeah, the takeaway is like, this piece of logic is not secured by the Polkadot or the relay chain, and you have to come up with a mechanism for your business use case that makes sure that, okay, whatever state changes that this particular the protocol or the business logic made, it's then secured by the relay chain. Yeah.
One more quick question. I joined a bit late, so you might have already answered this, but what's the difference between this and off-chain worker?
Yeah, that's a really good question. So off-chain worker, again, in a sense, it's constrained because it still requires, I mean, there are certain libraries that doesn't compile down to WASM. So off-chain, whatever you run in off-chain worker essentially should be compiled to a WASM blob for it to work. But in this case, that requirement is not there. You can basically have any library. Especially, for example, in Polkadex, we have like libraries that contact Intel servers for verifying the reports and by the enclaves. And that contains a lot of networking calls. Again, that's supported in off-chain worker. We can use that, but it only provides like REST or the HTTP calls. But that's not useful to this particular library or in our use case. Like it also has a lot of C dependencies and C++ dependencies, again, which doesn't work in the off-chain context. So if you have a library that you want to use in your business use case, and that doesn't compile down to WASM and a bunch of networking or other stuff, then you can use this model. And that's the difference between off-chain workers and this.
God, thank you.
Bradley, did you want to?
How does this model for dealing with off-chain work handle spam? So many very, say, expensive to process requests.
I didn't understand. Could you repeat?
This model for handling off-chain work, how does it deal with, say, spam? Many requests to handle very, very expensive work.
Yeah, I mean, that depends. In the example that I showed, there is no public-facing RPCs or endpoints, so there is no point of, there's no way to spam that. But if you do implement an RPC or an HTTP server with a validator, which you shouldn't do in the first place, do not expose validators. But if you do, then you have to come up with your own ways. It's basically like a different way of programming in Substrate. But again, it depends on your use case. Like if you are exposing an RPC, then you have to think about, should I do it in validators or should I do it in full node? So if you plan to do that, I would prefer it to have in a full node. The same way, the only difference is, like, I will show you that. So yeah, so here, instead of doing it inside the true branch of that if condition, do it in the else part, where basically it means that it's the full node. So full nodes can be exposed to the the public, and then there's no problem with that. So that's where you do it instead of the validator. So that way you can make structuring changes in your code, and then you can handle spam basically.
All right. Yeah. Thanks.
Anybody else? If no one else, thank you. Oh, just kidding, just kidding.
Hi.
Hi.
If the community is running collator nodes, does it depend on the goodwill of the person running the collator to have the correct logic when it comes
I
to...
can't hear. Can you repeat? I can't hear.
Yeah, because it's on the client, you cannot validate it on the relay chain. So are you depending on the goodwill of the collator or the person running the collator to have the correct code?
Yes, so we are depending on the collator because since let's assume all the blockchain projects are open source, so they can modify this particular piece of code and then run it part of the main network, and it will still work. But that's where you have to define some mechanism in the runtime so that you can catch such malicious behaviors and then figure it out. It depends on use case. For example, like in the example that I showed earlier, So let's assume that a malicious validator send a report that was not genuine, and it will get sent to the runtime, and then it will not get enough votes from other validators because we are assuming the game theoretic model here, right? Like majority are honest. If that is the case, the malicious report will not get enough votes, and then the runtime can have this. Like if a report was sent by somebody and it was not accepted because it didn't get enough votes to get the threshold, then who all voted for that particular report gets slashed. You can have that logic in your runtime and handle that malicious behavior.